So now that process that we just followed is presented as a pseudocode, so a very simple algorithm. And this is still, note, policy evaluation, right? So we're not actually improving a policy or taking actions here. We're just figuring out how much different actions are worth, right? The next step will be to add actions to this, don't worry. We will start doing something soon. So just to kind of turn that process that we had into code, you are given the policy, right? Because we said initially the policy was the random uniform policy, but it will be whatever you're currently using when you're learning. That's what you're evaluating. So you're essentially coming up with a value estimate of acting following that policy with all these assumptions of discounted reward and the model. So we initialize our array to 0, just like we said, and then we're repeating some delta here that we're going to keep track of. And so this is kind of our convergence score. And once this difference between the changing value gets to 0 or some small amount, that's when we're going to stop. So the process that we followed informally in the previous process here is kind of explained here, right? So you keep going until you're satisfied that the values aren't changing much anymore. As we said in the last panel, you're going to go to infinity, but in practice, you're never going to go to infinity. You have to stop. And the question is, when do you stop? Right? So the easiest way to stop is once all of the cells in the value table, which is represented by V. So we have an array in this formulation where the state has basically just an index, and the value table is just an array of numbers. And for every state, we're going to go through it, update its value. So we're going to pull out the current value in the table for that state, perform our update, and this would be carried out in code in a way that makes sense, iterating over all the possible actions, sampling the policy, and that will be done in code however it has to be based on how you're implementing it. You loop over all the actions that are available, sample the policy, and figure out how likely it is to pick that action to give you a probability, and sampling from, or reading off, the probability of that transition, using the reward, and using previously computed values in the table. Then once you've got this updated value for the entry in the table for state S, we need the difference, right? So that's why we had to store this value initially, because we're overwriting the value in our array, in our table here. Actually just overwrite it directly. But we need to remember what it was because we want to know how much it's changed, right? So every time we go through a round here, and remember each round here we're going through all the states, many of the numbers or all of the numbers will change, so we want to know how much. So that'll be delta, and we keep track of the biggest delta each time. And so here we're looping over S, and here we're looping over K in the previous slide, right? So we go through this as many times as needed, and once it gets below some small number, I wouldn't use theta. I would use epsilon for something small. Theta is usually a parameter these days. That's when you stop. This could be 0, so if you want perfect policy, you'd say this should be 0. That basically they've all stopped changing. Of course, on any computer that would only be up to your precision, right? So this could be 10 to the minus 9 or something, or 10 to the minus, I don't know, whatever your computer can do. But at some point, it's going to be essentially 0 and it'd be 0. And you don't really care about that level of precision. But theoretically, this goes to 0, and that's when it's the perfect value. And then the output you give is the last value function, and that represents the estimated value for the discounted returns for that policy. Right, so what we've done so far is kind of defined dynamic programming in using Bellman equations and given this kind of way of assessing the value of a policy itself. Now remember, before when we were talking about returns, we had the state value function, which we've just been talking about, and there's also the action value function. And I said they represent the same thing. It's still the discounted return. It's just indexed over state and action, which makes it actually very convenient to use. It has to store a lot more information, obviously, right? This is a table of S real numbers. This is a table of S times A real numbers, because we're storing all the combinations. But as we've now seen, this has S numbers, but it has them because each S is the sum over a bunch of A calculations, right? So they're just merged in, right? So this has less information than Q, in a way, even though it represents the same value. So for every state, you can work out V directly from Q, right? Have we seen how to do that yet? Right, you can think of that very easily. So think right now, just write it down. How do you compute V based on Q? You got 10 seconds. And I'll know if you don't do it right. So we're going to say S. It's going to be a particular S. We know S. Q is going to have an S. It's going to have some A. So what would you need to do? Right, so the value function without the action is basically this state Q function, the action value function, where we've chosen the best action, right? Because Q has access to all the value of being here, right? So you're in this particular spot for your robot, and you know that the value for this is that, it's like 1, that's -5, that's really bad. And Q has all of this, right? And so then you can say, well, you should go down, right? So max over all A of this Q over all the A would give you the down action, right? So assuming you have, for any policy you have, if you have a particular policy pi and the Q function for it, you can get the V function just by playing max on that. When we say Q star or V star, what does that mean, right? We talked about this before. Star is usually going to mean optimal for us in this course. So it's the one that's converged and become the single answer that's no longer changing, right? So once it goes to infinity, this one is the estimate that's star. Right, so we can represent V in terms of that Q, and then we can span out this way and say that one way to get V is to use the estimates of the transitions and V itself and maximize A. If we're using the action value function and we're learning, we come up with a different Bellman equation where we say that to compute this one, we put in the expectation of the reward plus the discount of the next step. And since it's Q, we don't know, because remember what this relationship is in the Bellman equation. This was just value of S, or in the original form of it, it was value S prime, right? That was how this part was represented, always with a gamma. But now with Q, we need to get as a value of a state, of being in that next state as t plus 1, given that you'll follow this policy into the future. So with Q, in this case, you have to pick that best action, right? So now we actually have to come up with A prime, which of course is AT plus 1, if you're being specific. to get the value there, and then you get the equivalent discounted expected return, right? The return of the next step plus a discount on the following step, and what you would do from then on, and this encapsulates all the returns going forward because it's recursive. And once we expand that out to the probabilities that we'll be getting, right, this return we're going to get at that point becomes the reward we get. Max is over the particular states, and the probability transition weights this. And so we get a different Bellman equation, right? So they're all still Bellman equations, they're just different forms of it. Great. So now we're then ready to begin improving our policy, because now we can compute the value of any policy we're given, pi, using Q or V, and Q is much more useful in a way because it has that action built in order to get the best action that we should take given a policy, pi, all we have to do is pick the action that's the best for that state. Right? If this is a good estimate of the value of being in that state and following the policy into the future, then when we pick the best action there, it should help us act pretty good at this point. Depends how good an estimate it is. So note here now we have the argmax, right? So we want to maximize this function, but what we want to return is the argument, a, not the actual value, right? Here we're saying max, and we want the actual value because that's going to be used to update and weight the value we're going to store in the table. Here we want to know which action gave you that, right? It's like an index request from an array rather than a value request. And so that will give us the updated value for this policy. This is just a very general way to think of it. Somehow your policy is being updated, so it's pi prime. But how you do this is what determines which algorithm you're using. The policy improvement theorem, though, says that as long as you keep doing this and choosing the best action given your estimate of value using that Bellman equation, where it's guaranteed that this greedy approach, okay, that's an important part. What we're doing here is we're saying this is greedy, just like we had in bandits, right? You're choosing the best action given what you know. That we guaranteed that we'll get a better policy if we follow this greedy approach of updating our policy, where better means that the value for the new policy will be higher than or equal to the value of the old policy, right? And so that literally means that here in these tables, these numbers should keep going up or staying put. If they stay put, it's fixed point, it's reached optimal, but they should always go up, otherwise they'll never go down. And that's just the way everything's structured. But there is a theorem showing that it basically, it will keep increasing. So you'll get to the optimal policy eventually, as long as it satisfies that structure. And once they're equal, so if you ever get to the point where they're actually equal, then we can call it star, assuming that the policy has changed. This is the best policy. So that would be our idea of optimality. And so this idea then permeates all of the reinforcement learning approach to decision making, because you essentially can cycle between your estimate of the policy. So everyone been talking about prediction or evaluation of a policy where you get V or Q, is taking an initial policy like the random one we had or something else, estimating a V pi 1 or a Q pi 1, and somehow choosing greedy actions from it to get a new policy, and then evaluating that one, because that one should have a different value, and keep going until it stops changing, right? Till that delta becomes less than some small number. And that's when you know, greedy, that you know you've converged. So any policy that you start with will evaluate to a unique value function. So there is a value function that gives you the correct evaluation of that policy. And then greedily choosing actions from that will give you a new policy which will be better than the previous one until you reach optimality. So if we've computed your value function for some deterministic policy in a simple domain, then the question is it better to use the action from that new policy? And the way you can do that is to figure out if the value you get for that action under Q is better than your evaluation for the entire state, right? And so if you don't have V being stored, then we do the same thing where we say that V equals essentially, sorry, not sum, max of A on Q, sorry. Right, we just use the existing Q that we have and evaluate the value of it, given all the actions. And if this one is better, then we'll update it, right? Because now we've essentially found an action that is better than some other action, A prime, that had a higher value before. But if there is some other action with a higher value, then this improvement doesn't necessarily help you because it's not beating something else that you know is better. And so this gives you the other direction. We had the way of computing V from Q. This one is giving you Q from V, right? So you could say that this is an expectation of the returns where the value in the next step is already figured out. We know the action is optimal. We don't even need to tell it to you because V has it all rolled in. So if you're doing that for Q, you still have to sum over the probabilities for the next step, but you don't need that max here, right? Because V already has it. So they're interchangeable in that way. So now, finally, we have everything we need to start building a policy improvement algorithm, right? So we're going to iteratively improve our policy using this action value function, Q, by choosing the maximum action. And we can even formulate it now into a way where the policy is related to an argmax action and a straight up value function. We're just estimating how good each state is, but then choosing the best action, right? So in this way, we're storing something simpler, but throwing away information about actions as we're going. But when we have to choose an action for a particular state S prime, for a particular state S, we can look at all the following states that could arise from it and then choose the action that is maximizing that. So in this step here, we're kind of also doing, like max has to loop over all the A's, right? So your complexity in this step alone is about A and S, because you have to go over all these A's and all these S's. Sorry, all these S primes. Right, so that's kind of the main idea. And once they've converged, then we must have the optimal policy. That's what the theorem tells us. So that once we follow this approach, if the V's stop changing, then our policy would stop changing and we'd have the right policy. So this gives us a way to build an algorithm called policy iteration. It's kind of a basic algorithm for RL, where you start with some policy randomly, evaluate what its value function looks like, evaluate all the different states and what would happen if you followed that policy, then greedify this value table to come up with a new policy that improves it, and evaluate that, and so on until you get to an optimal policy and an optimal evaluation, right? So if we go back to the problem we had before with the MDP and the initial, now it's just our initial policy of equiprobable random choices. So we can go in any direction, any of the 4 directions. Now our update is not going to be of V as much as we're going to be updating our model of what action we should take in every spot. In this case, we have to have representation for that policy, right? So we'll talk about a lot about different ways to represent a policy. One way to do that is simply to not represent it and only represent the value function. That's why people like the QSA representation, because if you store this, you can get the policy out of it very quickly just by doing max A, right? But if you want to theoretically build this using just a value function, you could have a representation of a table here too, right? So in this very simple domain, we'd have another policy where the policy pi is actually represented by a table, right? The same way as the value function. And in that table, you've got some representation of what actions you could take, right? I mean, this could actually be a string with all of your actions that are possible. And then as you go, when you get to the point where you realize, well, in this state, in this state here, there is one action that gets me much higher reward because it has less penalties, and that's to go down. And at some point, you remove all the others because they're not there. In some cases, 2 actions have a tie, their values are equal, and you still haven't ruled them out. So you have some representation where you can knock off actions and get rid of them for that explicit policy representation. But this Bellman equation tells you how to update what that best action should be in every state. And it might be a single action or it might be a bunch of ones. And so you can follow through if you, using the example we have here, and I encourage you to do that, is to go through this example and work some of these out. Why does this, we talked about why this was 1.75, right? And why that would mean that this is the optimal action, right? Because if you look at the values stored for each of the actions, the left action should have a higher number than the other ones. And if you take any point here where I give you this table and this policy, we should be able to say, well, how do you evaluate this policy to get the next table? Well, this isn't good. Nope, we jumped 10 ahead here. But if I gave you this table, we could compute this one, right? Any particular cell. Computing all of this by hand is not interesting. That's why we have computers. But seeing how these calculations work and why it makes sense is useful, because you have all the information you need here to do that. We know the probabilities and transitions. We know the possible actions. And so to update the value for the state, we can use this, right? So we know that it's going to choose to take one of these 2 actions, and we would use the value in the previous iteration here in order to come to the new valuation for that cell later on. And again, this is 7 steps later, but we could do that. I'm going to leave examples for the office hour event, but you guys can look through this and just explain more in the textbook. It's kind of a spatial example. It's a bit more interesting than Gridworld, and it has multiple levels of, again, this is a full representation of the policy, and I guess just policy, where you could represent which action is optimal depending on the state space, right? So how many cars are in each of the kind of 2 dealerships, how many should move between them. You usually can't represent a policy so directly as this, but it kind of helps us to understand what's happening. So the last thing to get to for this section, this chapter, is to talk about, well, there's one more part after, the two algorithms that come out of this. The first is policy iteration, which we've kind of talked about informally and seen, written out more as pseudocode. The pseudocode we talked about before was exactly this, right? So this is given a policy, evaluate it. I come up with that V. Initialization is just setting the values, introducing the value function to some numbers, and actions in the policy to some number. Again, we're using a table representation here for the policy. And now we've got this policy improvement step where we have some variable saying whether we've stabilized. Before we have delta. Here, whether the policy is stable is similar to that. Basically, has the action in that cell changed or not? And here we're not talking about, the difference in the value, because the actions in this domain, right, are literally up, down, left, right. And so the policy, every element of pi has a particular element that says you should take, right? That's the entry. If that changes, that means the policy is still not stable. And every time you go through all the states, something changes. It flips a bit, telling you which direction you should go if you're in a certain cell. But other than that, you just loop through all of the states, choose the action the policy should tell you. Again, this is deterministic, so it's kind of simpler. You then ask the policy what action you should take in that state. And if the actions don't agree, then you haven't finished, and you keep going. And so nothing is, well, I guess it is being changed here, right? Because in the policy, you've actually assigned the new action here, and you just note if it didn't change, then you'll go through this one time as a waste because there'll be no changes. You'll update them, but then you'd stop. So there'll be one wasted loop that wasn't strictly necessary. You needed it just to tell that you were done. So another way to find an optimal control policy here is to say that we're not going to use a policy at all. We're just going to do the best thing that we can see according to our current values. Right? So policy iteration uses this approach, right, where we update the value based on the optimal value and our current policy that we're using. Right, because it relies on that policy evaluation step. But another way to do it is just say, well, let's just start with some value function, random or 0 as we started in the other place, and then update that value function based on just the greedy policy. Take out the middleman, right? Rather than evaluating this particular policy and then choosing to act on it based on the greedy approach, and then going back and evaluating that new policy, we just say, find the max possible action given what we know, and then update the value estimate. And now we're estimating the value of being in a state, assuming you did the best possible thing according to your own value function. So there is an underlying policy here, but we don't really talk about it. We don't know what it is exactly. It's just the current policy, and it's changing constantly. So value iteration is another algorithm that will converge to optimal, and it's much shorter. It's not as efficient in terms of performance as policy evaluation. So it does essentially the same idea. You're going to repeat until convergence. You're watching for a difference between the current value of the function and the new one, which you've computed based on the dynamic programming record, and just maximizing the action, right? So when you're looking at the next action, you have to consider all of them, the likely following next state you'll end up in, and then look up the value for that next state, because you do have an estimate for that, even though you don't know what will happen after that. And again, once the value function's below epsilon or beta, then you stop. And then at the end, very end, after you've done this and you converge, and now you've got V star for S, for all of S actually, you now just say, we'll go through one more time, one loop through A, and for every state, pick the best action, right? And actually you have to do this for every state. So if you wanted to write it down as a table for every state, you'd have to go through every state, go through every action in that state, and just figure out the best one. Since this isn't a queue, you have to literally go through all the possible next states and next actions to get that. So yeah, so this is the sum over, for here you're going all A, and because of this part, because of this sum, you're going over all S, because of S prime. And then if you wanted to write it down for all of the states themselves, you'd have to do another S, right? So it's polynomial in the number of states to compute this, but that's if you want to go to kind of the perfect solution. So if we just go back to considering the difference between these two, policy iteration and value iteration, they both kind of do an exact solution, right? They find an optimal value function and thus an optimal policy. And they're very expensive computationally, right? Policy iteration tends to be a bit more converge faster, right? Because you're focusing on whether the policy converges, right? So once the actions have stopped changing, so that there's no, basically once you're close enough in your value function estimate so that the policy doesn't have to change, you can stop, right? Whereas in value iteration, you don't stop until the value function itself stops changing, right? And you can imagine that in a domain like anything. So if you come here, we can look at and see that after 3 iterations, we already had the optimal policy, right? Even after we do 10 and infinity, something went wrong with the PDF here, the value functions changed until they converged to these numbers, but the policy didn't, right? We'd gotten to the point here where it was good enough to know that if you're here, you should go that way, and if you're here, you should go that way, and then you should go that way. And knowing these numbers more precisely and all the trade-off didn't make any difference to the fact of what you do when you're here, right? So the bar for stopping for policy iteration is often not as high as for value iteration. I actually should write it higher, right? So we start off with policy is kind of random, and at some point this will be good enough and we'll have that, right? But getting to V star is actually a lot harder, and if all you care about is an optimal policy, this is all you need, right? And these algorithms are, as I said, exact, right? So most of our stuff is going to be not focusing on exact, we're going to approximate, but this general intuition is still kind of generally true. Many of the popular methods focus on optimizing the policy in a way that's more efficient so that when it's good enough to act, that's when you stop. Whereas optimizing these values estimates is something that could go on forever. So I think I'll stop there, and there's a little bit more to say about these examples and general policy iteration. Maybe we'll talk about those things during the office hour on Wednesday and see if people had a chance to see these videos or not. So see you then.